Hello and welcome back to Advent of Code 2014. We're on to day 15. We're halfway through the month. It's been pretty interesting so far. I mean, this ink code thing is quite interesting because it builds up. This hasn't been done in any previous year that I've done before, where you have a program and you continuously modify it over like half the days. So 15. Oh, of course, here we go. It's an int code problem. So the last one was 13, right? So that's the one we'll reuse. Okay. All right, I'll just grab my coffee and let's start on day 15 then. Okay. Day 15, oxygen system. Out here in deep space, many things can go wrong. Fortunately, many of those things have indicator lights. Unfortunately, one of those lights is lit. The oxygen system for part of the ship has failed. This reminded me of Faster Than Light, the game. According to the readouts, the oxygen system must have failed days ago after a rupture in oxygen tank 2. Oh, this is very Faster Than Light. That section of the ship was automatically sealed once oxygen levels went dangerously low. A single remotely operated repair droid is your only option for fixing the oxygen system. Okay. The Elves care package included an int code program, your puzzle input, that you can use to remotely control the repair droid. By running that program, you can direct the repair droid to the oxygen system and fix the problem. The remote control program executes the following steps in a loop forever. Accept a movement command. Send the movement command to the repair droid. Wait for the repair droid to finish the movement operation. Report on the status of the repair droid via an output instruction. Okay. Only 4 movement commands are understood. North 1, South 2, West 3, and East 4. Any other command is invalid. The movements differ in direction, but not in distance. In a long enough east-west hallway, a series of commands like this would leave the repair droid back where it started. Okay. The repair droid can reply with any of the following status codes. 0 if they hit a wall. 1 if they've moved 1 step. 2 if they've reached the oxygen system. Okay. You don't know anything about the area around the repair droid, but you can figure it out by watching the status codes. For example, we can draw the area using D for the droid, hash for walls, dot for locations the droid can traverse, and empty space for unexplored locations. Then the initial state looks like this. To make the droid go north, send it 1. If it replies with 0, you know that location is a wall and the droid didn't move. So if you... Alright. What is the fewest number of movement commands required to move the repair droid from its starting position to the location of the oxygen system? So once we know where the oxygen system is, then it would just be breadth first search, wouldn't it? Okay. Well, so in each step we kind of just want to find the nearest unknown location. It's an infinite grid, is it? Okay, so fine. The only thing we need to deal with is we would have to, because it's an unbounded grid, so it'd be initialized with like no locations, but we could put a bunch of unknowns. Okay, right. I have an idea. So we need to import encode. Okay. Okay, so let's say position equals 0, 0. There's no notion of direction. Actually, there is. Sort of, but we don't store a direction for the robot. Okay, so we've got when we've decided which way we want him to go. Well, okay, so let's say we have grid equals default dict int, so everything is 0. We'll use 0 for empty space. No, 0 for unknown. Yeah, 0 for unknown. Let's just make a note here. 0 for unknown. 1 for floor. 2 for wall. Okay. Okay. And then we need a couple of helper methods. So define get neighbors of a specific position. For delta in, let's say, -1, 0, 1, 0. Zero, -1, 0, 1. Yield P0 plus delta 0 P1 plus delta 1. Let's define distance between P1 and P2. Returns, it's going to be the absolute value of P2 0 minus P1 0 plus the absolute value of p2 1 minus p1 1. So that's distance. What else do we need? So put this down here. So we need to put some stuff in the grid, some unknowns, because it's completely empty. Well, position 0, 0 is a floor. So grid dot add pause. Wait, grid pause equals 1. And we need to initialize all the things around it. So for neighbor in get neighbors pause, just do this. Grid neighbor. This seemingly does nothing, but it creates the side effect. So the IDE complains, but I believe it should have the side effect of adding those to the grid if they're not already in there. That's the key. So we're not overwriting anything, but if it's not in there, we set it unknown. So if we do that step there, okay, so while true. In every step, we want, okay, so we need to initialize the int code. So it's just going to be like this. Okay. So for each we need BFS here. So BFS is just going to tell us the distance to a goal and the next step to take. Because for all we know, they could make a maze and then you have to wind around to find it near goal. All right, so BFS, so it's just standard BFS. So we do Q import Q. Q equals Q dot put start. So we want dist equals distance table. Oh, we're gonna need a came from map as well. All right, well. Okay, so while Q dot while not Q dot empty current equals Q dot get All right, so for neighbor in get neighbors of current. All right, if neighbor in dist, skip this one. If neighbor, if get neighbors, no, if, all right, well, this needs to be up here. If rid neighbor is not a floor, skip this one. So it's a floor. We haven't visited it before. So it's the new neighbor, so we put dist neighbor is whatever the distance was to the current plus 1. Because it's BFS, the first time we see something will be the shortest time we visit that. Came from neighbor equals current q dot put neighbor. If neighbor is goal, right, so well, that's not where we want to break, is it? Because then, all right, no, we won't do it there. If we expand it, if current equals goal, break, all right. All right, so if we reach this point, I mean, the things we're running this on, it should never exhaust the queue. All right, we should always find a way to get to a location. So, so then we need to know the next step to take from where we are. That's all we need. So temp equals goal while came from temp is not equal to start. Temp equals came from temp. So just backtrack until you've got temp being the next one after start. And then we return temp and distance to goal. Two things we need from BFS. All right. So okay, so in one iteration, we're going to pick one unknown. So we're going to pick the closest unknown. So candidate equals min of, it's going to be grid.keys. We map a key to, it's going to be the distance from our current position to the to that key well, hang on. It's gonna have to be like k for k in grid.keys if grid k equals 0. We only want the unknowns. And then we map key to the distance to that key. So we take the minimum. Okay. So next step equals BFS from where we are to this candidate. Delta equals, it's going to be basically next step 0 minus pos 0. So this is just the vector, the unit vector. So the command, so direction input equals, so it's gonna have to be, you're gonna have to map this. So say, so let's have a look. So they said north is 1. All right, we'll go with that. 0, 1 goes to 1. 0 minus 1 goes to 2. Minus 1, 0 goes to 3. 1, 0 goes to 4. So we take that delta, map it to our direction input, and then we do int code dot put input direction input. Is that right? Then we just wait for the output. Result equals int code dot get output. Okay, so what do we do with that output? If it's 0, it hit a wall. Okay, so if result is 0, then it's told us all the only information that's changed is that whatever's in front of us is a wall. So we say grid next step equals a wall, which was 2. Okay. elif. All right, so that's the easy bit. If it says 1, then it's moved 1 step. So either way, it's moved one step. So it's else pause equals next step. So we're now standing on next step. So that means grid of where we're standing now must be floor. And for neighbor in get neighbors pause, let's just initialize everything just in case. So it'll be grid neighbor. And then what else? If it's a 2 specifically, then we found the goal. If result is 2, goal equals pause break. So I'll break out of this while true loop. I haven't tested any of this. Should I try running it? Kira -10. Yeah. Came from temp is not equal to start. It says there is no came from for -10. Well, oh, one thing I need to check. If grid neighbor is not equal to 1, there is one exception here. We're allowed to step into an unknown if it's the final step. So if neighbor equals goal or that. Oh, no. If neighbor is not equal to goal and if it's not the goal and it's not a floor. Tuple and int. Next step. Just take the first parameter of this. Okay, it ran. Alright, so finally, we have a goal. So we want to print BFS from the start to a goal. Just take the second parameter. That should be the distance. 298. Correct. Let me just turn the AC on. Alright, you quickly repair the oxygen system. Oxygen gradually fills the area. Oh my god, this is exactly faster than light. Oxygen starts in the location containing the repaired oxygen system. It takes 1 minute for oxygen to spread to all open locations that are adjacent to a location that already contains oxygen. Diagonal locations are not adjacent. Suppose you've used the droid to explore the area fully and have the following map. So in this example, all locations contain oxygen after 4 minutes. How many minutes will it take to fill with oxygen? So we're just trying to find the furthest point from the goal. So we could just run BFS a bunch of times. Right, well, the first step is to run this exhaustively. So we don't want to... So we say oxygen equals pause, but we don't break. Just do it as normal. Okay, so here, candidate, so if all grid if all v is not equal to 0 for v in grid dot values break. Right, so we should just exhaust the whole thing now. All right. So that means there are no unknowns now. We've completely surrounded by walls. So we could just run an exhaustive. Let's see what it looks like. Well, that means we can just exhaust. We can just do print. So we have the maximum of the BFS from oxygen to a location. Just take the second parameter here. For P in grid dot keys if grid P is 1, it's a floor. So we're taking the floor which has the highest BFS distance. Now this is inefficient because you're running BFS over and over again. What you should be doing is one flood fill. Can't be bothered to do that. So let's run it then. Aim from temp is not equal to start. What's happened? VFX from oxygen to P. P in grid dot keys. If grid P is 1, that means it's a floor. It could only be a floor if we've actually found a way to get there. So what's happened here is we've not found the goal. So goal is temp is none. So goal was never initialized. So we never found a way to... So basically this queue emptied and we didn't find a way to get to that location. Oh. Maybe there's one case where you're trying to move to your own cell. Let's just say if start equals goal. Yeah, because then the way I did the came from doesn't make sense. Alright, so if start equals goal, return. Return, I don't know, start 0. Three, 4, 6. That's the furthest distance. I mean, that could pretty easily be done without having to do a BFS. Just every time we do BF. Oh. Yeah, but it has to be from the oxygen. But yeah, you can just do a flood fill. One flood fill, which does an exhaustive BFS, but... I mean, the flood fill is BFS. We have BFS staring at us in the face, so if we had a parameter saying no goal... then... yeah, it doesn't matter. Let's see if it's the answer. Just do it without a goal, then it could do it a different way, and just Is it 1 minute per? Okay. Correct. That's it. 15. That was nice, straightforward BFS. 16. Oh, looks like some sort of cryptographic thingy. Alright. Hang on. Okay, your flawed frequency transmission. You're 3/4, 3/4 of the way through the gas giants. 3/4. Okay. Gas giants. Oh yeah, because we're at the gas giants, which are... which ones are the gas giants? Jupiter, Saturn. Ah, so Uranus and Neptune used to be gas giants, but now they're ice giants? Okay. Astronomy keeps changing. Not in my day. Alright. Not only do round-trip signals to Earth take 5 hours, but the signal quality is quite bad as well. You can clean up the signal with the flawed frequency transmission algorithm, or FFT. Is this fast Fourier transform? As input, FFT takes a list of numbers. In the signal you received, your puzzle input, each number is a single digit. Data like 15243 represents the sequence 15243. Okay. FFT operates in repeated phases. In each phase, a new list is constructed with the same length as the input list. Wait, so the... Okay. So we've got a sequence of integers. This new list is also used as the input for the next phase. All right. Each element in the new list is built by multiplying every value in the input list by a value in the repeating pattern, then adding up the results. Oh, I'm guessing this is going to be like we have to find a sequence really far ahead. All right. Adding up the results. So if the input list were 98765 and the pattern were 123, the result would be this. Okay. Only the ones digit is kept. So fine, even if it's negative. How could it be negative? Oh, the pattern could be... The pattern is integers. Okay. When each element in the output array uses all of the same input array elements, the actual repeating pattern to use depends on which output element is being calculated. The base pattern is 0, 1, 0, -1. Then repeat each value in the pattern a number of times equal to the position in the output list being considered. What? Repeat each value in the pattern a number of times equal to the position in the output list being considered. So, for the first... What do you mean being considered? Ah, okay, so doing this sum here gives us one element in the new list. And to get the next element in the new list, we adjust the repeating pattern and do it again. When applying the pattern, skip the very first value exactly once. So for the second element... What? So for the second element of the output list, the actual pattern used would be this. Okay. So if the base pattern... But doesn't that mean we should skip the 0 of the base pattern? Or maybe not, I don't know. No, I think just the second. Okay. After using this process to calculate each element of the output list, the phase is complete, and the output list of this phase is used as the new input list for the next phase, if any. Given the input signal 1, 2, 3, 4, 5, 6, 7, 8, below are 4 phases of FFT. Within each phase, each output digit is calculated on a single line with a... Alright. So the initial pattern is... the base pattern 0, 1, 0, -1. Oh, but you do cut off the 0. Okay, so... So you keep the 0 for the purposes of getting the next pattern, but when you apply the pattern, you ignore the first digit. So it's 1, 0, -1. Then the next pattern will be 0, 0, 1, 1, 0, 0, but you cut off the 0, so it's 0, 1, 1, 0, 0, -1, -1. Okay, got it. Okay. Here are the first 8 digits of the final output list after 100 phases for some larger inputs. Computationally, is this going to take a long time? We're talking... each digit... each digit of the new input takes a linear time to process this. So basically, one phase would mean so getting one element would mean a linear time. So getting one full output would be quadratic time, and then multiply that by 100. I think that's all right, but it's quite long, but it's we can do it. Okay. Interesting. Okay, so we just want to sequence equals int x for x in f dot read line dot strip. Okay, so it's a list of integers. So let's make some methods here. So define FFT given an input list, let's say array, and a repeating pattern. We'll want to spit out the new array. FFT operates in repeated phases. Okay. All right, so should I call it? Let's just call it phase, because FFT describes the whole collection of phases, I suppose. Okay, so how do we do one phase? So we're given a pattern. We so just say new pattern equals pattern 1 onwards, because we need to chop off the indices to work here. So we chop off the first character. And then we're going to do the sum of it's going to be sum of, so it's going to be, hang on. So if I is the index, it's going to be array I times pattern I % length of new pattern. So that should be new pattern. So that restricts to that region for I in range length array. So, with that sum, then we only take the, so we take the absolute value of it, so it's positive or non-negative. And then we do mod 10 to get the units digit. So result equals list result dot append that. And then wait, so okay. This is not a phase. This is just FFT. So we've got a base pattern, and then we've got pattern equals base pattern. I don't want to change the original. And then pattern to use equals that. So we're gonna have to do this. We're going to do for, let's say j in length in range length array. Doesn't actually matter what j is. We take pattern. No, this is okay. This is the initial thing. So pattern to use is that, blah, blah, blah. I'll do that. And then after this, we want to change the pattern, expand the pattern. Is there an efficient way to do this? Can we just Just temp equals this for x in so what we're using pattern temp dot append x temp dot append x twice. Is that no is that repeat each value in the pattern a number of times equal to the position in the output list being considered? Oh. Okay, fine. We don't need to do that. We do need J here. So pattern to use equals. So it's going to be this. So we don't base pattern. Just we don't need to change that. Just say pattern. All right. Okay, pattern to use is an empty list for x in base in pattern. Pattern dot use dot append x, but we want to do it for j time. So to begin with, j will be 1. J will be 0. So we do j plus 1 to get 1. And then pattern to use, just delete the first one. That's how we construct the pattern. So the base pattern never changes, but we construct each time. So it'll start with 1, 1, 1, 1 of each, and then 2 of each, and so on. Okay. Result is just that. Result dot append that. Okay. Let's test this out. So we've got a sequence. Or should we just jump straight to the answer? Let's say for in range 100. So we want sequence equals FFT of sequence with the base pattern. So it was 0, 1, 0, minus 1. 0, 1, 0, minus 1. Then the first 8 digits in the final output list. So print dot join string x for x in sequence up to 8. Okay. None object has no length, because we never returned the result. Alright, hope it's right. Took a few seconds, but I don't think there's any way of skipping steps there. You have to just do all that. It's too high. Oh dear. Alright, let's try input signal. Just this one. Just do 1 phase. 3, 8. 38226158. It should be 48226158. How am I one off in that digit? So the first number should be so you should get 4. Should be using 1 0 minus 1 0. So I haven't added one of the digits. So how did I get a 3 instead of a 4? Is it the first pattern to use for x in pattern for that in range j plus 1? So when j is 0, to use append x. Just I don't know. Print pattern to use 1 0 minus 1. Oh. You just... Oh, I see. When you use the repeating pattern, you discard the first element, but you still repeat as if it was there. So actually, what you should do is... this. Pattern to use... Oops, I'm on the wrong window. Pattern to use equals... pattern to use 1 onwards plus, so it's as if you inserted it at the end. Like that. You just rotate it by 1. Four eight two two 6158. Okay, that's correct. Okay. We want to do this 100 times. Okay. Correct. Now that your FFT is working, you can decode the real signal. The real signal is your puzzle input repeated 10,000 times. Treat this new signal as a single input list. Patterns are still calculated as before, and 100 phases of FFT are still applied. Right, there's no way we can run this as is. We'd have to hmm. We don't need to calculate the full number. We just need... You need all the digits for... So the first 7 digits are the location of the 8-digit message. The number of digits to skip before reading the 8-digit message. Here is the 8-digit message in the final output list after 10 phases. Right, there's some ways we can speed this up. But so if we look at this pattern, you're ignoring, whenever there's a 0, you're ignoring those elements. Whenever there's a 1, you're adding those elements, and whenever there's a -1, you're subtracting those elements. So it's kind of like yeah, but that only means half of them are cut out. That's not that much, but... is there, we don't really need to calculate this pattern every time, do we? Can we just, if we knew that... Can we just immediately calculate what... We can, can't we? So if it was... If we didn't cut off the first element, let's consider that case first. Then if you wanted the like position, if you wanted. Well, it doesn't harm us to make the patterns. But how many patterns do we have to make? 10,000? Suppose we could do that. But, it'd be 10,000 patterns, so it's gonna be like in the millions. But if we initialize them all, then we'll never have to make them again. Let's try that first. I'm not sure how to speed this up yet. So let's initialize a pattern list. So it's going to be the J determines which pattern you use. So it's going to be, let's say, patterns equals that. So n equals length of sequence times 10,000. So they're saying multiply whatever here by 10,000. Wait, so what is that? It's actually 6 million. Bloody hell. That's even worse. Oh, man. Okay. So I think the fact that it's repeating is important, because all that matters is which pattern, which index of the pattern you start at, right? And then the next chunk will have a different sum. Ah, I see, I see. So we have the pattern, we get the sum. Now we're doing this 10,000 times more, right? When we're computing this sum. However, we just have to calculate what it would be like at starting at a certain... Okay, so consider this. In this pattern, we have this pattern, right? But we start from index 1. For some reason, we skip 0. So we start from index 1. And that gets us a certain sum. If we had started from 0, we would get a different sum. If we had started from 2, 3, and so on, we would start from a different sum. Every one of these 10,000s is just going to be one of those. So we just have to compute the sum for each element of the pattern. And then for each of the 10,000, we just recall that value, that sum value from the from that table. Furthermore, that sequence itself is just going to be a repeating pattern, but that doesn't matter so much. So let's say we memorize. This is memorization basically. So we define a method here. Define get pattern sum for a given index. All right. Yeah, I think this will be efficient. So we basically do this sum here. But we want to memorize. So if index in table, return table index, result equals this, sum of array I times, no, we don't do this, we do no more pattern, no more messing around with these pattern to users. In fact, that was a waste. We do pattern. So it's going to be index plus I. I don't know why I didn't do this to begin with. Percent length pattern. Table result equal the table index equals result, return result. Okay, so now get rid of all this. This should be faster now even for part 1, so let's try that. Result dot append, so take this out. So it'd be the absolute value of get pattern sum starting from index 1, not 0. All right, try that now. Array I times... Oh, fuck, because you still need... Ah! Because you do actually still need the... Oh, this needs to be per J. Fine. This is because it's going to be different for you. It's different pattern. Okay, fine. Do it like this. So we do actually need... We're using pattern to use, not... but we do use that, so get pattern sum 1. Try that. That should still be faster, but it's no, it shouldn't be faster. It should just be the same. We're just doing one sum once. Oh, bloody hell, we get a different value now. Sum of array times pattern to use. So it's going to be index plus I Oh, because I chopped off the thing, didn't I? So we don't need that. Starting from 1. 440982. 440982. Okay, so we've got the same result. Now, how do we use this? So now, for each of these, we're going to spend 10,000 steps, though. There is a way to speed this up, but I don't know if we'll actually need it. But anyway. Also, these can be stored beforehand. Because they're going to be the same for every iteration, aren't they? So let's try that. So patterns equals that. So it's going to be like this. Put J in range, so it's going to be N. Oh, hang on. But what about the extra? The array is bigger now. Oh no, this is so confusing. This only works for the first for the first n characters, first n positions, then afterwards you're using a larger sequence, but this is really weird. Okay, it's fine. I think basically you need a method. You forget about all these patterns and everything. You just need a method which says, given your position, I want to know if it's the 1 or the -1 or the 0. Because there's just 4. So first you want to find, okay, so we know the length of what the length of the pattern would be. Okay, hang on. Okay. Define, we don't need to mess around making patterns. Let's say define get, so that what we use the pattern for is to get the 1 or the -1, right? Or the 0. And if we knew how many times something's going to appear with the 1, how many times it's going to get the -1, then we'd know how many times it appears, wouldn't we? But that's a different story. Okay. This is basically matrix multiplication, isn't it? We're actually multiplying matrix whose rows are the repeating patterns by but we can't use numpy or something for that because the matrix would be too big. Okay, just continue with what I was doing here. So for so I'm saying, okay, get rid of this. Define get pattern value for a given output index, all right, for a given array input index. We want the value. It's going to be a -1 or a +1 or a 0, essentially. So how do we do this? So if the index is so it's basically the output index +1. It's that many repeats of the 0s, the 1s. Okay, so the length, so base pattern length equals output index +1 times 4. Right, because of the 0, the 1, the 1, the 0, the -1, so Okay. Well, let's store this base pattern here. So it's, what is it? 0, 1, 0, -1. Okay, times length of base pattern. So this is not base pattern, this is scaled pattern length. So scale pattern length is going to be that times the length of the base pattern. All right. So the index scaled pattern index equals input index sent scale pattern length. All right. But because we've offset it, we have to add 1. So if we were looking at the first array, we would get index 0 here. But because we want to start from the index 1 in the pattern, we add 1. So we add 1 here, actually, not there. So that's the scaled pattern. That's the index in the scaled pattern. So base pattern index equals scaled pattern index divided by this, essentially. So it was scaled up to 3. Let's say it's scaled up to 3. I want to divide by 3 again to get whatever the index was here. So if for example we had 0, 0, 0, oh, yeah, 0, 1, 1, 1, 0, 0, 0, -1, and so on. Let's say we were here. Our index would be 1, 2, 3, 4. 4 divided by 4 is 1, rounded down. So that would give us the 1. Okay, so that's it, right? We return base. That wasn't that complicated. It took me a while to think about it. Now we don't need to mess around with any patterns. It's pure arithmetic here. So we want get pattern value. So get rid of this. To get rid of all this stuff. Okay, so pattern sum equals it's gonna be essentially this, but this bit here is just get pattern value. So the output index is J. The input index is I. All right, let's see if that actually gives us the answer. The same answers before. What's it doing? 44098,263. It still took around the same time, but I mean, this is much cleaner. No more having to deal with patterns. Okay, so that's the start. So this is quadratic. Now what? I reckon this is more about if we knew this. So, although this entire sequence is going to be millions long, we can calculate all the prefix sums. So we know the sum of every prefix of it, and from that we can effectively get the sum of every slice in constant time and when we need it, right? Why would we need that? But because this pattern has got a bunch of ones and a bunch of minus ones, so essentially you want to so you want to, if this was a whole bunch of zeros and a whole bunch of ones and a whole bunch of zeros and a whole bunch of minus ones, you would want, when you're applying this pattern to the array, you would have a contiguous subarray where you're just adding all those elements together. Similarly here, you get a minus here. So you don't need to add all those things individually and have to call this every time. So actually we don't need this if we're going down this route. Instead, we should be adding chunks. That reduces everything to chunks, so that eliminates a large factor. Let's try that. So how do we do that? Basically, we would first we need to compute all the prefix sums. Let's try that. So for x in sequence. Hang on. Yeah, but then we need this for every. We need this for every step of the FFT, don't we? Well, we can do that, but it doesn't need. It shouldn't be done here. It should be done here. Okay, prefix sums then. For x in array prefix sums dot append whatever the last value was plus x. So if you want to fetch the sum from index 0 to index 2, say, you would call prefix sums 2. And that would basically include the 2 elements. All right. Let's just see how much longer that takes now. But now we'll use this to speed up the... Okay, not much longer. All right, now we can use this. So we can say... Okay, let's try a different approach here. So we say, so we've got J is the output index. So repeated length equals J plus 1. That's the base pattern's repetition length. So let's start with a base pattern. So base pattern index equals 0. We start with the first thing in the base pattern index, and when it comes to summing the input, we do input. So it'd be input index equals 0. All right. While input index is less than length of. All right. So we're running through the input index. We're adding chunks using this repeated length. So and we're skipping the zeros, so we're actually going to cut out a lot of work here. So if base pattern, so that if the value is not equal to 0, then we do this. So hello, DJ. 15. I did question 15, which was pretty easy, just searching through a grid, which we do so many times in these problems. I'm now on a pretty tricky cryptography one, which involves a sequence which is 6 million in length, and we need to find some way of encoding it 100 times in a row. I think the way to speed it up is to look for sequences of repeated sequences and simplify them. So, let's see if that's not 0. We're gonna do, right, so total equals 0. Num repeated equals j plus 1 if input index is greater than 0. So normally we use j plus 1. Get rid of this. But if we're starting, we actually have to use j. Just because of that weird one-off that they did just to throw us off. Okay. That's the num repeated. So we want to get the sum of elements from... So slice sum equals. So it's going to be prefix sums up to... Hang on. Slice end will be input index plus num repeated, but we have to round down to in case it overflows the array. So do minimum of that and length of array. So that's the slice end. So the slice sum is prefix sums slice end minus prefix sums of the input index. So that's the slice sum. Total, add the slice sum. Okay, and then in either case we want to go to the next base pattern index. Oh, well, we have to actually multiply this by the base. Alright. And then here move to the next base pattern, the input index is going to have to change, so... that is computed no matter what. So slice end will be the new input index. Slice end. Okay, so that's all the things being changed, and so the idea is that we would end up with the total after that. So then we would add abs of the total %10. All right. Hopefully get the same result. It takes a while to compute the prefix sums, that's the problem. But I would have thought it'd be faster overall once we've done the prefix sums. Wait, no, it shouldn't take long to compute it. It's a linear search through the array. Alright, it's stuck somewhere. While input index is less than length array. Index equals slice end. Oh. Ah, no, this logic is not right. It's... Okay. First equals true. Can't think of another way to do this. Just do that. And say, if... So on the first iteration, we just have to subtract 1. First... num repeated -1. First equals false. Minus equal. So we just have to cut off that one element on the first iteration. So it was an infinite loop. There we go. 44098263. And that was faster. Much faster than before. So now we can discard that. Now, can we run this on our big pattern? So that is part 1. Part 2. So it's still gonna take too long though, isn't it? But it's... can see how many iterations we can get through, but it's... No, we're gonna need something else. Just try it anyway. So... So we're going to start with sequence equals the original sequence, so... 650. So here... The problem is these... right, whatever. So this is going to have to be multiplied by 10,000. That's crazy. It's going to be too big. And then print I. Try to apply. We don't need this parameter anymore. I am range 100, okay. So it's stuck on the first iteration. We have to do that 100 times. Fine. We have to eliminate this 10,000 factor because it's just repeated. Whenever something's repeated, usually there's a shortcut. We can check if it's probably the right answer though by testing against the examples. Let's see. Okay, so use this input. That's taking a while, isn't it? Well, we can try and leave it running, but that's not fast enough. Okay, so now what? I don't think I can finish this right now. I might have to continue next time. Unless I can quickly think of something. So we have an efficient way of using the pattern, so that is no longer... The problem here really is this is going up incrementally linear time. Now, we shouldn't really need to have to do that. Well, we kind of do... No, it feels like we do because... Okay, go back to what I was thinking earlier about this 10,000 business. So... Hang on. Ultimately, we still need to make an array of millions long eventually, because don't you need that for the next iteration? Like, there's no way you could avoid that, could you? Well, using the... I have a sort of idea, but it's a bit weird. Alright, I think it's something to do with... Alright, so... This huge sequence is repeated 10,000 times. No, I thought I had something, but the base pattern repeats also up to that many times, so like there could be like 6 million zeros in a row. Which is weird. Excuse me. Should we just at least run it on 100, like we were just doing now? Wait, but we still need to do the final bit. So once you've got the... Okay, so you need to take the first 7 digits of the input Okay, so the offset tells you the location of the 8-digit message. So message equals, so it's going to be this. So it's going to be offset plus 8. So if I run this and let it run to 100, we should hopefully get the answer. That means it's correct. Oh. Oh, I see. Okay, just let it run to 100. That will mean our logic is correct. We just need to find a way to reduce it by a factor of 10,000, essentially. So we know what the offset is to begin with. So we know where in that message, in that sequence is the message. So can we get away with not computing the millions of other digits? It's tricky because you use all those digits to create the next iteration of the message. But this is a tough one. How do people find it? Let's have a look. 16. Yeah, it's harder because there's more people who did silver but not gold. Even though it looks like it's easier, but it's just because more people got stuck on silver. And part 1 was fine. Took about 20 minutes for them to solve this. Up to an hour. Alright, if I get this right, then I might just call the stream here and continue next time. Alright, let's see. This is just for the sample input. So the real input is just massive. 20 minutes is a long time for first done. Yeah. Last advent of code, I think 1 or 2 of the problems took up to about 40 minutes to an hour for some people to solve. Those are really hard. .00442, is that what they have? No, it's not. Damn it. So it's not even correct. It's slow and incorrect. Alright, well, we've got a lot of work to do next time. Oh, fuck. We're using the wrong sequence. This seq is the result of previous part before we reset it. That could be it, or it could not be. Could be another problem. Let's test it. We're using the wrong seq. Okay, now we've reset seq. Now we're using that seq. Alright. Hello, lazy Aseku. Alright, so I'll just wait for this to run again. Look at it go, yeah, it's racing through those numbers. This is really... There must be some really clever trick to this. FFT, I think it's a reference to fast Fourier transform, which is not actually what we're doing here. But it could be a hint. Oh, it's... I can't remember. It's been a long time since I did Fourier transforms. It's more of a electronics thing, but alright. I think that's enough coding for today. Mostly. And come on. I'm gonna be thinking about this all night long if I don't solve it today. Which I'm not planning to, so. I'm just wondering if you could do something clever with matrices, but I don't think so. It's like you'd have matrices which are millions in width. Oh, man. What? I got 00442480 again? How? But they was using a different sequence. So it should have been different. No, the same sequence, different offset. How could it be the same? Oh man, what? They could have given us a simpler input than this. So I don't have to wait forever for it to run. What on earth? So print my sequence equals FFT sequence. Four, 462. Nope, that's nowhere near what we're supposed to get. It's 10,000. Yeah, but I mean, these numbers don't matter. How could it be? Is FFT always using arrow and not something else? Yeah. So what for the first answer we get 2, 4, 4, 6, 5, 7, 9, 9. Wait, what? No, that's wrong as well. I've broken part 1. No, I haven't. That's for the bit the example input. All right, we'll worry about this another time. It's just broken in many ways now. I mean, if I were back working in the office, I would end up staying late into the night just because you never want to leave your code in a broken state, but not anymore. Alright. Well, that was day 15 and partial 16. I guess I might be back on tomorrow. Or I might take a break because that's been like 4 days straight of Advent of Code. And it's not exactly Christmas, so I don't have to punish myself this much. Yeah, I'll have a think about this in the meantime. Thanks for stopping by, Lazy. Are you doing anything Advent of Code or anything like this? Do you know what Advent of Code is? But we've got another coding competition coming up, which is coding game. Oh, but I don't think it's the good kind of competition. I think they're doing the boring one, which is the you just know about it today, and definitely we'll try that out. I think it's like the best educational resource for programming there is now. Like, a lot of these big corporation sites have gone not great. They've gone like, you can see from the front pages, they've gone into marketing. And they used to be great. They used to be the kings of learning algorithms. Now it's this site, all made by one guy who really has enthusiasm about his site, and he doesn't want to turn it into this. That being said, I do like coding game. It's great, but you can see these sites are becoming very corporate. I can't even see from here without logging in. I can't even see the problems. It's just a lot of advertising for companies and stuff. Anyway, see ya, Hex, take a break with something soothing like that pinball game. I beat the pinball game yesterday, and I was about to give up and add it to my list of games that I will never finish. But I did actually beat it. It was it was an ordeal. But despite how frustrating it was, I did actually enjoy it. So I could actually see myself playing it again in the future. It's weird. It's just the right level of frustrating where you're not actually losing too much when you lose, sort of. I nominated it for the Wheel of Struggle, and during that stream, I was actually regretting it. I was like, oh no, if this comes up on the wheel, I've basically made myself play another 5 hours of this. But now that I've beaten it, I feel a bit better about it. It is a... And yesterday my mic wasn't working as well as it was in previous sessions. I guess I might need to adjust the mic for the volume or something. I just got to play the entirety of Monkey Ball. We had Super Monkey Ball 2 on the Wheel of Struggle. It was pretty good. But it's a bit fast-paced for my taste. I think inevitably another Monkey Ball game might come up on the wheel, but speaking of the wheel, it's now over. Wheelofstruggle.com. No, it's not over. There's one more round, which is the Forgotten round, which means if there's a game that someone hasn't played in the previous weeks, then they can now do this in the Forgotten round. But because I don't have one that I haven't participated, I played every game, therefore I can't do anything for the Forgotten round. And you get the points you would have gotten if you had been in the leaderboard at that time. So it's like a time warp leaderboard. Aptly named since you forgot it. But yeah, I played every game, even the ones I hated the most, which were Earthworm Jim, Sonic CD, and E.T. E.T. wasn't as bad, though. I think Sonic CD was the one I just disliked the most. The ones which were the surprises to me that I actually liked, despite the fact I don't like the genres, were Dynamite Headdy, Zombies Ate My Neighbors, and Pepsi Man. They were actually decent games, and I don't normally play those genres, and I don't normally like those genres. Has anyone nominated Zelda CD1? CDI? What does that stand for? There have been a bunch of Zelda games nominated. Let me take a quick look. We've got Zelda Link to the Past, Zelda 2. I guess that's it. Oh, it's in an infographic, so I have to... Ocarina of Time. Those three. The Philips CDI, the meme Zelda games. I don't know anything about those, but if it's not one of those, then no. It's ones with the really bad animations. I think it would be good for me to play Link to the Past because it's such a popular game and I don't really play that kind of game, but it's required playing, I would say. So, especially as it's got lots of randomizers and speedrunning tournaments and multi-world, it makes it more feasible for me to actually watch people run those and actually know what they're doing. Okay, that's it. So, thanks again. See you guys next time, probably in a couple of days' time. Bye-bye.